The hydrostatic equation. In this video we're going to derive this equation and use it to make sensible statements about the vertical structure of the atmosphere. In particular, what we can say is that a fluid is in hydrostatic equilibrium when each small cylinder within it has zero total force on it. Applied to the real atmosphere, what this means is that the atmosphere doesn't fly off into space. There's a balance of forces so that there's zero net acceleration. Consider now a fluid of density ρ. Consider inside that fluid a subvolume in the form of a cylinder with a cross-sectional area A and a height delta Z. Height Z increases upwards, and we can also define the unit vector k, which is the vector of length 1, pointing in the Z direction. Now the two forces acting upon the cylinder are the gravitational force and the pressure gradient force. The gravitational force is the sum of the gravitational constant g and the mass, and gravity acts downwards, so that's minus gk, and the mass is equal to m. But we have a fluid of density ρ, so the mass of the cylinder inside this fluid is ρ by v, where v is the volume of a cylinder, and the volume of the cylinder is the cross-sectional area A by its height delta Z. So that's the third expression in the gravitational force, minus A delta Z rho g in the k direction. The pressure gradient force is the difference between the pressure force, which is A by P, at the bottom of the cylinder minus A of P at the top of the cylinder. The pressure at the bottom of the cylinder is P of Z, and the pressure at the top of the cylinder is P of Z plus delta Z. So we end up with the expression shown there, AP of Z at K by K minus AP of Z plus delta Z by K. We then take out a factor of minus A delta Z in common with our expression for the gravitational force, and so we have to, inside the brackets, have a delta Z on the denominator. And because we've taken out the minus sign, that rearranges the two terms, so we now have a P of Z plus delta Z minus P of Z over delta Z. And in a minute we'll take the differential limit and see what that produces. So to get the total force acting upon the cylinder, we add these two terms together. We have the common factor of minus A delta Z outside the brackets, which is the volume, or minus the volume of the cylinder. And inside we have the sum of the pressure gradient, which is pressure at the top minus pressure at the bottom divided through by the height of the cylinder, plus rho g, which is the gravitational force. And the second expression on this slide is simply dividing through by the volume of the cylinder, which is A by delta Z. So we have a pressure gradient force and a gravitational force. What we do now is take the differential limit as delta Z approaches 0. And when you do that, we get in the limit that delta Z equals to 0, or goes to 0, the force per unit volume is minus dp dz plus rho g in the k direction. Remember, the original goal was to find the balance of forces such that there's no net force or no net acceleration, so f of t is equal to 0, which means that the terms inside the bracket must balance to 0, so we have dp dz as minus rho g. This is the hydrostatic equation. What does this mean? Well, as intimated before, dp dz is the pressure gradient in the vertical, and because we can equate the pressure at a depth in a fluid as equal to the mass of the column of fluid above it, it means that pressure decreases naturally with height. So that would say that it was a pressure gradient force upwards. So in theory the atmosphere should just fly away, but that pressure gradient force is balanced by the force due to gravity. And so that gives us this balance of forces, dp dz, as minus rho g, hydrostatic equilibrium. We can now combine the hydrostatic equation with the equation of state, or the ideal gas equation, written in terms of the density ρ as equal to P on RT, and substitute that into the hydrostatic equation, and we can write dp dz is equal to minus rho g is equal to minus Pg on RT. Next step, divide both sides of the equation by the pressure, and so on the left hand side we have 1 on P dp dz, and on the right hand side we have minus g on RT. Now dp on P is equal to d log P, the natural logarithm of P, And if you need to, go and stop the video and revise natural logarithms and natural exponents. So that the term on the left hand side now may be written as d by dz of log p. So we can integrate that with respect to z. But we can't automatically do that for the right hand side of the equation because in general the temperature will be a function of height. So we'll make an assumption here. The assumption will be that we can have some kind of average value for a layer of atmosphere for the temperature, and we'll call it T bar, so that the right hand side might be written as approximately equal to minus g on r T bar. And so now we can integrate with respect to height both sides of that equation. That's what's shown here in the top equation. The integral of d by dz of log p dz is equal to the integral of minus g on r T bar dz. So the left hand side integrates to log p, and the right hand side we have minus g on r T bar by z, and a constant of integration k. If you then take the natural exponent of both sides, e to the power of log p just gives us p, and then we have e to the power of k minus g r T bar by z, and using fundamental exponential identities we can write that as e to the k multiplied by e to the minus g on r T bar by z, and e to the k we'll call p naught, some reference pressure. So that gives us the equation there for pressure with height, and so of course in this case p naught will be the pressure when z is equal to 0, because e to the 0 is 1. We can then work out what's known as a scale height, which gives us a measure of the depth of the atmosphere. R T bar on G for T of about 273 is equal to 8,000, which is 8 kilometers. So for T is 273 Kelvin, we can write our equation as P is equal to P naught, the surface pressure, the exponential of minus Z in kilometers divided through by 8, which is our scale height. Below 100 kilometers, T is approximately equal to 255 Kelvin, plus or minus 15%. So with this equation for the vertical structure of pressure with our scale height, we can plot that, and that's the red line, the thin red line, and then the thick red line is mean conditions. So you can see how well the hydrostatic equation, when integrated to give us the vertical structure of pressure with height, closely matches that for that scale height. Now, dp dz is equal to minus rho g means that the pressure at a height z is equal to g by the integral of rho dz, and we've used z dash as a dummy variable, from z to infinity. So the hydrostatic pressure is equal in magnitude to the weight of the atmosphere above that level, as I stated earlier. But if the pressure is equal to the weight of the column of atmosphere above, then in the situation shown here, when a plane flies overhead, why aren't people crushed? Go away and have a think about that.